Our last example on this handout is function j of x, which is the cube root of x plus 3. So although it's written in Mathematica with the cube root in words, this is the way we would see it written on paper. And so again, I start by plotting the function just to get a sense of what it looks like. And this is the cube root of x function shifted 3 units to the left. It looks like it doesn't have any maxes or mins. It appears that it's concave up and then switches to concave down. So it seems like there's a point of inflection at x equal -3. And that also looks like a place where the tangent line is vertical. So the derivative maybe is not defined. So I'm looking at the function and kind of trying to assess it just visually first, and then I'm going to use Mathematica and my understanding of derivatives to confirm or deny those ideas that I came up with. So as per usual, we start by taking the first derivative of j, and again, Mathematica understands the prime notation. Notice what happens when I try to set that equal to 0. I get an empty set. And then I look back at j prime and I say, oh yeah, I guess that makes sense. J prime is a fraction, and a fraction can only equal 0 when the numerator is 0. And since the numerator is +1, the numerator will never equal 0. So j prime never equals 0. However, I remember that to find critical numbers, I want to find not only where the derivative equals 0, but where it's undefined. And where this fraction will be undefined is where its denominator is 0. So I use the solve command on the denominator of j prime and set that to 0, and I get x equal -3. So this is a critical number, or we sometimes say critical point. They're interchangeable. Now, FYI, in this case, in the solve command, using the denominator call worked. Sometimes that does not work, and you have to actually copy the expression. Copy this, whoops. You may have to, in future ones that you work on, you may have to copy and paste this expression in place of the denominator of j prime of x. I have found that sometimes the denominator and numerator commands work, and sometimes they don't inside the solve command. So just be aware. Okay, so I'm using a table here, and I'm going to look at j prime on either side of this critical value. By the way, x equal -3 is a critical value because it is in the domain of j. Remember, in order to be a critical number, that x value has to be in the domain of the function. In this case, that x equal -3 is in the domain of j, so it is a critical point or a critical number. And so I see here j prime positive, meaning j is increasing when x is to the left of -3. And then I test a point to the right of -3. I tried x equal -2, and I got another positive value, so j prime is increasing there. And oh, complex infinity when x equals -3. So again, j prime of -3 is not defined. I found that out with my solve command, where I set the denominator equal to 0. That would mean the first derivative is undefined where its denominator is 0. And here this just reinforces. I get complex infinity as my value of j prime of -3. Again, reminding me that derivative is not defined at -3. Then I look at the second derivative, j double prime of x. And again, I want to set that equal to 0, and I see I get the empty set. J double prime does not equal 0. But I also want to look at where the second derivative is undefined to find possible inflection points, and I see that happens at x equal -3. So this is a potential point of inflection. And what I want to do is check and see, does the second derivative change its sign, sign, on either side of that x value? So I set up another table, and I pick an x value to the left of negative 3, and I picked negative 4, and I see j double prime is positive, so that tells me that j is concave up to the left of negative 3. Then I pick an x value to the right of negative 3. I picked negative 2, and I evaluated j double prime there, and I got a negative number, which tells me that j is concave down to the right of negative 3. And again, this complex infinity, j double prime of negative 3 is not defined, but that's okay. In fact, j of x has an inflection point at x equal negative 3, because on either side of that, the second derivative changes its sign. So even though the second derivative is not defined at x equal negative 3, that's okay. I still have an inflection point on j at x equal negative 3. So j prime of negative 3 not defined, and I see from my picture I have a vertical tangent line, which I had seen earlier, and the derivative is the slope of the tangent line. If the tangent line is vertical, that means its slope is undefined, so the derivative is undefined. And I found a point of inflection at x equal negative 3 by the fact that the second derivative changes sign on either side of that. So to the left of x equal negative 3, j is concave up, j double prime is positive, j prime is increasing. It would be interesting to look at the graph of j prime and j double prime. You could do that as well. To the right of x equal negative 3, j is concave down, j double prime is negative, j prime would be decreasing. This m, slope of the tangent line at x equals 3, is undefined. Vertical lines have undefined slope. Again, that reminds me j prime of negative 3 is not defined. But I do have a point of inflection on j at x equal negative 3.